Hi class, welcome to Unit C, Concept 2, Standard Deviation and Z-score. This is a normal curve, or it's also called a normal distribution, and it represents naturally occurring data such as height. Most people are near the average, and that's in the middle, and very few people are very tall or very short, and those would be represented at the end. So on a normal curve, the mean and the median are the exact same number and is represented by a line here in the middle. So draw this in on your picture. For simplicity's sake, let's say that the average height is 5'6", and this is the mean. This symbol here is mu, it's a Greek letter, and it's going to represent our mean. The normal curve is divided into sections, and these sections are determined by the standard deviation. I'm going to show you how to find the standard deviation in your calculator in class. But all a standard deviation is, it tells you how far away from the mean a data point is going to fall. So our standard deviation, let's just say, is 6 inches. Is represented by another Greek letter called sigma. So we're going to now label each section. One standard deviation above the mean, I'm just going to take 6 inches and add it to my mean, and that's going to give me 6 feet. I'm going to do that again and take another, add on another standard deviation, so that's going to be 6 feet 6 inches. And then 3 standard deviations away from the mean is going to be at 7 feet. It also works in reverse. So on the left-hand side, I'm now going to subtract the standard deviation from the mean. So 5'6" minus 6 inches is 5 feet. Another standard deviation away is going to be 4 feet 6 inches. And then the last one is going to be 4 feet tall. So let's talk about what each section represents. 68% of the data, or people, are between 5 feet and 6 feet tall. That's this area I'm highlighting right here. 95.2% of the people are in between 2 standard deviations away, so between 4 feet 6 inches and 6 feet 6 inches. And then almost everyone in the population, 99.7% of people, are between 4 feet tall and 7 feet tall. You can see there's a tiny little bit over here on the ends, and those are going to be even more standard deviations away. There are extremely few people beyond these heights. Another way to look at where a data point falls is the z-score, and all a z-score is, it's the number of standard deviations away from the mean. So we can label each of these sections in the following z-scores. The mean is 0 standard deviations away from itself. This line right here is going to be a z-score of 1 because it's 1 standard deviation away. And then the next line is going to be 2 standard deviations away from the mean. And this last one at 7 feet is going to be a z-score of 3 standard deviations. It also works in reverse. On the left-hand side, it's going to be standard deviations that are smaller than the mean. So I'm going to represent those with negative numbers. So -1, -2, and -3. Now we're going to calculate how to find a z-score using some information that's given to us. Up here at the top we have our z-score formula. So the z represents the z-score, the x represents our data point, the mu, remember that represents our mean, and the sigma represents our standard deviation. So all we're going to do now is just read our problem and then substitute information into our formula. So we have Amy and Abby taking a biology test. The class's mean is 75, that's our mu. And the standard deviation is 6.5, that's our sigma. What is Abby's z-score if her score was 84%? So in other words, that means find her z-score. So now we're just going to take our formula and substitute in values that we know. Trying to find our z-score, so that stays z. X is our data point, 84, minus our mean, 75, divided by our standard deviation, 6.5. Remember, order of operations tells us to do the top first, so 84 minus 75 is 9, and 9 divided by 6.5. If you put that in your calculator, you're going to get an ugly decimal. Well, this is one of the few times that it's okay to round instead of using a fraction. So round it to 2 places. Abby's z-score is 1.38. Let's look at part B. It says Amy's z-score was negative 0.25. What was her test score? Well, the fact that it's a negative number tells me that my answer is going to have to be less than our mean. So let's fill in our information into our formula. We know what the z-score is. That's negative 2.5. We don't know what her test score is. That's what the question's asking. The mean is 75. And our standard deviation is 6.5. Okay. How are we going to solve an equation like this? I've got x in the numerator, right up here, and I need to get rid of this 6.5. And how do we do that? That's right, we're going to multiply both sides by the denominator. So we have negative 1.625 is going to equal x minus 75. Okay, and then now all we're going to do is add 75 to both sides. So our data point, or Amy's score, test score, is going to be 73.375. All right, now it's your turn to use the formula to find some z-scores. So go ahead and hit pause so you can get a chance to substitute the information into the formula and answer the questions. Okay, so reading the problem, we have a mean weight of 4 pounds, so that's our mu, and our standard deviation of 0.25, so that's our sigma. So for part A, Z is, let's see, the bass weighs 3.6 pounds, so that's our data point, minus our mean, divided by our standard deviation. 3.6 minus 4 gives us negative 0.4 at the top. And when we divide, we get negative 1.6. So this makes sense because our bass was less than our mean, which means we'll end up with a negative standard negative z-score, negative standard deviations. So how about part B? It says, what would the score of a 4.5 pound bass be? So z equals 4.5 minus our mean, divided by our standard deviation. We get 0.5 at the top. Divided by 0.25 is 2. So remember that this is above the mean. It's 2 standard deviations, so this bass is very large compared with other bass in this population. All right, don't forget to write your summary, and we're going to work on coming up with some good questions next class. See you then.